Physics is the branch of science that studies matter, energy, and the fundamental forces of nature. Father of physics, Isaac Newton gave 3 simple laws that explain almost everything that moves. Objects like to keep doing what they're doing. If they are sitting still, they stay still. If they're moving, they keep moving unless something else makes them stop or go faster. That's Newton's first law, sometimes also called law of inertia. Second law is all about force and mass. The harder you push, the faster something moves. But if it's really heavy, it takes more force. So, if you want to launch a rocket, you need a lot of force to get that off the ground. Newton's third law is quite funny. For every action, there's an equal and opposite reaction. This means if you push something, it pushes back with the same force. That's why rockets fly, because the burning fuel pushes downward, and the rocket zooms upward in response. Mass and weight are related but distinct concepts. Mass is the amount of matter in an object. It remains constant regardless of location and is measured in kilograms or grams. Mass is a scalar quantity, meaning it has only magnitude and no direction. But weight is the force exerted by gravity on an object's mass. It can vary depending on the strength of the gravitational field. Weight is measured in newtons and is a vector quantity, meaning it has both magnitude and direction. An object with the same mass, like 10 kilograms, will have different weights on Earth and the Moon because the gravitational pull is different on each. On Earth, the object will weigh more due to stronger gravity, and on the Moon, it will weigh much less due to weaker gravity. Now let's focus on energy. In physics, energy comes in many forms, but 2 of the most important types are kinetic and potential energy. Kinetic energy is the energy of movement. If something is moving, it's having kinetic energy. Whether it's a speeding car, a flying soccer ball, kinetic energy is all about motion. The faster you go, the more kinetic energy you have. On the other hand, potential energy is stored energy. Imagine standing at the top of that roller coaster. You're not moving yet, but you're loaded with potential energy. The higher you are, the more potential energy it has. As soon as you start moving down that roller coaster, that potential energy transforms into kinetic energy. But remember that energy never disappears. It just changes from one form to another. This is called the conservation of energy. I think it's good time to move towards thermodynamics. It is the branch that deals with heat and temperature. Heat is a type of energy, and it always flows from something hot to cold. If you pour a hot cup of coffee, but after a while, it cools down. What's happening there, actually, the heat from the coffee is escaping into the cooler air around it. This is called heat transfer, and it happens in 3 ways: conduction, convection, and radiation. In conduction, heat moves through direct contact, like when you touch a hot stove and immediately pull your hand away. Convection is when heat moves through fluids like air or water. This is why hot air balloons rise. The hot air inside the balloon is less dense than the cool air around it, so it floats up. Finally, radiation is heat transfer through electromagnetic waves, like how the sun heats up the Earth from millions of miles away. The laws of thermodynamics tell us that heat energy cannot be created or destroyed just like any other form of energy. It can only move around and change forms, so it means that energy is conserved. Waves are one way to transfer energy from one place to another. Actually, a wave is a disturbance that moves through space or a material without carrying matter along with it. Think of waves as the ripples you see when you drop a stone into water. Those ripples move across the water, but the water itself doesn't travel with them. Waves can exist in different forms, and the 2 main types are mechanical waves and electromagnetic waves. Mechanical waves need something to travel through, like air, water, or solids. A common example is sound. When you speak, your voice creates vibrations that travel through the air, letting others hear you. Mechanical waves can be transverse or longitudinal. In transverse waves, the motion of the wave is at a right angle to the direction it travels. A good example is the waves you see on the surface of a pond. In longitudinal waves, the wave moves in the same direction as the vibration, like sound waves or compressions you feel in a spring. Electromagnetic waves, on the other hand, don't need any material to travel. They can even move through the vacuum of space. These waves are formed by electric and magnetic fields moving together. Examples include light, radio signals, and microwaves. This is why we can see sunlight even though space is mostly empty. Momentum is a key concept in physics that helps us understand how objects move and interact. Momentum is the quantity of motion an object has. It depends on 2 things: how much mass the object has and how fast it's moving. If a heavy truck is moving at a high speed, it has a lot of momentum, which makes it harder to stop. In contrast, a light bicycle going at the same speed has much less momentum and is easier to stop. Momentum is calculated by multiplying an object's mass by its velocity. You must have hit unintentionally to the wall or anything else. Actually, it's collision. When two or more objects hit each other, it's called collision. Law of conservation of momentum states that the total momentum of a system before and after collision is the same, as long as no external forces like friction act on the system. Collisions can be of two types, elastic and inelastic. In an elastic collision, objects bounce off each other without losing energy. For example, if two balls collide, they keep moving in different directions. In an inelastic collision, objects may stick together or deform, losing some energy in the form of heat or sound. A car crash is an example where two vehicles might crumple and slow down. Entropy is a tricky concept in physics. Entropy measures the amount of disorder in a system. Think of it as a way to understand how ordered or disordered something is. In a perfectly ordered system, like a clean desk with everything in place, the entropy is low. But in a messy room with items scattered everywhere, the entropy is high because there's more disorder. The universe naturally tends to move toward higher entropy. That means, over time, things tend to become more disordered. For example, if you leave a pile of papers untouched on a desk, they're more likely to get messier than magically organize themselves. It's not true that all time entropy of system increases. Sometimes processes decrease entropy too. For example, water freezing into ice. In liquid form, the water molecules are free to move around, which is a more disordered state. But when water freezes, the molecules lock into a structured, solid form. This decreases the entropy because the system becomes more ordered. However, overall, the entropy of the universe still increases because heat is released into the surroundings during freezing, adding disorder elsewhere. So, one part of a system can become more ordered. The total entropy keeps rising. Now, let's move to quantum mechanics. It is a branch of physics that explores the behavior of very tiny particles, like atoms, and the particles inside them. On this small scale, the rules of classical physics, which explain how big objects like cars and planets move, don't apply. One of the key ideas in quantum mechanics is wave-particle duality. This means that particles, like electrons and even light, can behave both as particles and as waves, depending on how we observe them. For example, light can act like a wave when it travels and spreads out, but it can also act like a particle called a photon when it hits something or is detected. This is very different from our everyday experience, where objects are either particles or waves, but not both. Quantum mechanics also tells how particles behave at the atomic level. Particles like electrons don't follow definite paths like planets orbiting the sun. Their positions and speeds are uncertain, and we can only predict where they might be with probabilities. This is explained by Heisenberg's uncertainty principle, which states that we can't know both the exact position and momentum of a particle at the same time. Quantum mechanics also introduces the concept of quantization, where particles can only have specific fixed amounts of energy. This explains why atoms have energy levels, where electrons can jump between levels, but electrons cannot exist between these energy levels. An electric field is the area around a charged object where other charges can feel a force. The stronger the charge, the stronger the electric field. When we connect charged objects through a wire, we create an electric circuit. In a circuit, electric charges or electrons flow from one point to another, powering devices like lights and computers. To understand how circuits work, we use Ohm's law, which explains the relationship between voltage, current, and resistance. It's simple, actually. Voltage pushes the current through the circuit, and resistance tries to slow it down. Now, let's talk about magnetism. Magnetism is a force caused by moving electric charges. A magnetic field is created around objects like magnets or wires carrying current. In fact, electricity and magnetism are deeply connected. Electromagnetism shows how electric currents can produce magnetic fields and how changing magnetic fields can create electric currents. This principle is used in many technologies like motors, generators, and transformers. Einstein's theory of special relativity changed the way we understand space, time, and motion. It focuses on what happens when objects move at very high speeds, close to the speed of light. One of the key ideas of special relativity is that the laws of physics are the same for everyone, no matter how fast they are moving, as long as they are moving at constant speeds. One of the strange effects of special relativity is time dilation. This means that time slows down for an object moving at very high speeds compared to someone at rest. For example, if an astronaut traveled at close to the speed of light, time would pass slower for them than for people on Earth. When they return, they would be younger than if they had stayed on Earth. In length contraction, objects moving at high speeds appear shorter in the direction of motion to someone watching from a stationary point. This means that the faster an object moves, the more it seems to shrink along its path. Einstein also gave famous mass-energy relationships, E equals mc squared. This means that mass and energy are two forms of the same thing. Even a small amount of mass can be converted into a huge amount of energy, which is the principle behind nuclear energy. To understand nuclear physics, we need to have clear concept of atomic structure. At the center of atoms is a nucleus, which is made up of protons and neutrons. Protons have a positive charge, while neutrons have no charge at all and they're neutral. Surrounding the nucleus are electrons, which have a negative charge and move around in energy levels. But inside protons and neutrons, there are even smaller particles called quarks. These quarks are held together by the strong force, keeping the nucleus stable. Isotopes are atoms of the same element that have different numbers of neutrons. Most elements have stable isotopes, but some have too many or few neutrons. This makes the nucleus unstable, and due to this reason, the atom can undergo radioactive decay. The term decay means when the unstable atom releases energy in the form of radiation, trying to become more stable. Another important term is half-life, and it is the time that radioactive atoms takes for half of a radioactive substance to decay. Different isotopes have different half-lives, some lasting seconds, others millions of years. The shorter the half-life, the quicker the isotope decays. This concept helps us understand the stability of isotopes. Isotopes with longer half-lives are more stable, while those with short half-lives decay rapidly. Radioactive decay is a natural process that plays a huge role in areas like nuclear energy and carbon dating. Now we can move to nuclear fission and fusion concept. Both these processes release huge amounts of energy. Fission is when the nucleus of a large atom, like uranium, splits into smaller pieces. This splitting releases a lot of energy because breaking apart the strong forces inside the nucleus frees up stored energy. Nuclear fission process is used in nuclear power plants, where we control the process to generate electricity. On the other hand, nuclear fusion is when two small atomic nuclei, like hydrogen, smash together to form a bigger nucleus. This process also releases a ton of energy. Fusion is the same reaction that powers the sun and other stars, where hydrogen atoms fuse to form helium. Fusion produces more energy than fission and doesn't create long-lasting radioactive waste. In both fission and fusion, there's a key concept called a mass defect. This means that the total mass of the particles before the reaction is slightly more than the mass after the reaction. Where does that missing mass go? It's converted into energy. This is explained by Einstein's famous equation, E equals mc squared, which shows that even a tiny amount of mass can be turned into a large amount of energy. I hope you have enjoyed the video and it will be helpful for you. Let me know which part was best one. And also, don't forget to like the video and subscribe my channel for more such educational videos to help you in science subjects. Wishing you all the best. You can also check other videos on my channel to help you out in chemistry subject. See you in next video.